Think about it. Math parody of the movie Jaws. I'm going to need a bigger eraser. All right. Can't make an eraser too big. This one actually. So if you want to see my scratch, there you go. That's me just trying to do it in my head. But what you should get is this comes out. All right, here's the after the product roll. Is that cool? Oh, can you turn? Thanks, Cole. Oh, thank you. Cool. Is it ever cool that first line? That's what you get immediately after taking the derivative, right? Chain rule, product rule kind of stuff happens. Then you can take out a 2. You can take 3 of these out and 4 of those out. Bam. So then you're left with 4 times, 2 times this. This is me trying to skip and make 2 times 2x plus 3 is 4x plus 6. Here you're left with 5 times one of these, so you get 5x minus 15. So then inside there you'll get 9x minus 9. Take a 9 out, that makes 18. Bam, bam. And then you're left with the next minus 1 there. Alright, should be something you could just sink your teeth into. Just do it. I think some of you guys see the answer and you think you're going the wrong way, but it's one of those problems. It's not going to look like it's supposed to until you're almost there. You can't do that to yourself. Just do what you know is right. Okay, so now that we got that, check. Critical numbers. What are all the critical numbers?
3, negative 3 halves, and 1.
Take the ash, just set that equal to 0. It's all factors. Beautiful. And now I can do my sign diagram. There's negative 3 halves. There's 1. There's 3. I love it when people put those out of order. And then it just, nothing quite works right. So now if I plug in, I can plug 0 in, that's nice. And then I can use multiplicities. I'm going to try to get you guys to do that. That makes this kind of problem so quick. If I plug a 0 and I get positive times negative, I get positive times negative times positive. What's 0, Jeff? Times negative. So I get positive, negative, I get positive in there. Woo! The only piece that's negative will be that negative 3 cubed. And the minus 1. So you get 2 negatives, 2 positives, so the whole thing's positive. How's that? Multiplicities. This one's got an even multiplicity around this, so it's going to stay the same sign on both sides. It's going to turn. I don't know if you guys remember that. Right? And then the other 2 are odd, so it's going to change signs around those. Now, if you don't trust me, you can just do test points in each one and eventually get to those answers.
We owe your TC.
How did you just decide it was a negative there? Although you...
I didn't. Do you understand multiplicities?
No.
Okay, that's where we start. That's the question, because I'm using multiplicities. So the fact that this is cubed, and this is to the first power, they're going to do like odd polynomials do. They go through their roots. So if it's negative on one side, it's going to be positive on the other. So anywhere that's an odd multiplicity, it's going to change signs around that root. And anywhere there's an even multiplicity, it's going to do like a parabola. It's going to stay the same sign on both sides of the root. And again, if you don't understand the shortcut, don't use it. Just check. Like we did 0, just check in every single little region. Just check something. That's all. Get the same answer. Just take longer. So what intervals? Let me add something I haven't done yet. What intervals is it increasing on? Do it what?
1. So 1.
Where's it start increasing? Negative infinity. Okay. Negative infinity up to what?
1.
Negative 3 halves, because it's flat there, so it can't be increasing there. Or negative 3 halves up to 1. Or 3 to 3. So the only place it's decreasing is 1 to 3. Kick ass. So I will ask that kind of question. Tell me the intervals on which it's increasing and decreasing. And you just got to look. Is it a plus sign or a minus sign? It's that simple. Right? Because all the work went into making this thing. Now tell me, are there any local maxes? Which one is the local max? Or how many? Sorry. I gave it away. So there's one local max, it's at 1 something. How about the mins?
I'm supposed to.
Yeah, 3. Because the other things, this guy is that little, tricky thing. He looked like he was going to turn this, and now I'm not going to turn. So now I can just figure out, I just plug those into the original function to figure out what they're. When I plug a 3 in, I get 0, of course, it's nice. That's nice. I'm sorry. Thank you. And when I plug a 1 in, I get something. 16 times 5 to the 5th. I get something stupid big.
5,000.
5,000? Exactly? Late. Sorry, didn't mean to get so excited. Alright. I like it. So real quick. Too bad for you. Ha ha ha. What we're going to do next is kind of funny. There's something called Rolle's theorem that says, now what do you think about this? What do you think? If I had a continuous function from A to B, and f of A equals f of B, it could be a straight line. If it's not a straight line, if it's a straight line, obviously the slope between A and B is the same as the slope everywhere on that line. Now watch this. The slope between A and B, what is the slope between A and B? What's the slope of that line? 0. So Rolle's theorem says if you have the same beginning and ending value on a continuous function, there's at least one place in the middle where the slope is 0. And if you think about it, that just makes freaking sense. If it's not a straight line, if it starts to go away, it eventually has to turn back around so it can come back to B. So on one level, it's like, good job, Roll, wherever you are. The proof of it takes a while, but the idea of it just makes sense. And the mean value theorem is a more general thing than this. So that's section 4.2. So we'll do that tomorrow.
Huh?